So now we will discuss a problem related to the slab base. So here the question is given to design a slab base or a base plate for a ISHB 350 at 661 Newton per meter column to carry a factor load of 1500 kilonewton. So we have to assume a Fe 410 grade steel, an M25 concrete, and also design the welded connection between the steel column and base plate. So the base plates are provided beneath the bottom just above the pedestal to connect a column to the concrete pedestal. So this will be a compression member, and we assume the load to be purely compressive in nature. So the given data here is we have to assume the grade of steel as 410, which means the ultimate strength of the member will be 410 Newton per mm square, and the yield strength of the member will be 250 Newton per millimeter square. So M25 grade concrete means the design compressive strength FCK value will be 25 Newton per mm square. The factor load is given as 1500 itself, so no need to multiply. So the factor load will be 1500 kilonewton, which will be 1500 × Newton. Now we have to write the properties of the column section. So based on the properties of column section, we will be designing the slab base. So ISHB 350 at 661 Newton per meter. So if you are using our IS 808 1980s version, so it is given in kilogram per meter. So roughly 661 Newton per meter means 67.4 kilogram per meter. So and this will be the first ISHB section. Okay, that will be that. So based on that, we have to write the following properties. So when we go to IS 808 in that's older version, the steel table, it is given in page number 5. Otherwise you have to go to heavy angle I sections, you will be getting this value. So there will be this designation. This is the mass 67.4, this is the sectional area which is 85.9 in centimeter square, and remaining all values are majority of the values are given in mm. That is total height, which is d only. So there is a figure. Height means the total depth, which is 350. B is the total width of the member, which is 250, and TF means it's the thickness of the flange, which is 11.6 mm, and TW is the thickness of the web, that is the middle portion, which is 8.3 mm. So these are the major things which we have to obtain from the steel table for our calculation for the design of slab base. So after that, we have to find the bearing capacity of the concrete. So the bearing capacity of the concrete, because slab base basically has to bear the load, so it is given as 0.45 times the design compressive strength. So this is actually given in clause 7.4.1, where the resistance, that is the shear resistance at the proper contact surface between the steel base and a concrete ground, may be calculated using a friction coefficient of 0.45. So we have to factor that. So we have to apply a friction coefficient of 0.45 multiplied by our design compressive, that is multiplied by the M25, which is 25 only. So when we multiply, we will obtain a value of 11.25. Now we will be using these values to design our slab base. So we have to design the dimensions of the slab base, that is the length and breadth of the slab base, and also we have to design the thickness of slab base. So what will be our required area? Our required area will be, we know that factor load divided by bearing pressure. So basically, what is stress load by area? So area will be load by stress. Here the stress that is occurring between the connection between the column and the base plate will be a bearing pressure, which we calculate as 11.25. So when we take the ratio, we obtained an area of 1.3 into 10 raised to 5 millimeter square. So this is a value I have converted in terms of power. So what we have to do that, so that has to be the total area of the base plate. So this is the figure of the base plate. Okay, and base plates are usually fixed using an anchor bolt of 20 mm diameter. So we have to have that idea in mind. So this is also very important. So we assume a projection of A on both sides on the along the length and as well as along the width. So along the length, we have to assume a projection of A here. So the total length L now will be the base plate will be the total width of this our I section plus 2A, and also the total width B will be also 2A plus the total width of the I section. So we know that the L of the I section is 350 and the width is 250. So the net length of the base plate will be 350 plus 2A and 250 plus 2A. So the area will be length into breadth. So we have to multiply these two values, 350 plus 2A multiplied by 250 plus 2A, and this will give you our required area. So we actually calculate the required area just before from the factor load divided by bearing pressure, and this was 1.333 into 10 raised to 5. So I substitute the value of required area in this value and I solve this. So this will become a quadratic equation. So you have to open this bracket. 2a is 4a square. Now what is this value? 350 into 250 will be 87500, and this we have to multiply here. So this will be 2a into 250, which is 500, and also 2a into 350, 700. So it will be 1200. Now this is a constant. We have to this here, and this value minus this value will be 11458.33. Now the value of this, the whole thing has to be divided by 4 also. So 1.3 10 raised to 5 minus 875 divided by 4. So to eliminate this value, the whole equation was divided by 4 also. So to obtain this quadratic equation, we can either use your calculator to solve this problem, or we can use the quadratic equation for the value of a. So here a is the variable coefficient, minus b plus or minus root of b square minus 4ac divided by 2a. So don't get confused. Usually it was x, now it become a. So when we solve this, you will getting a value of a as 34.27. So this is the projection which we required on the both sides. Now we have to check whether this projection is enough or not. The thing is that we have to provide anchor bolt for fixing our base plate to the pedestal, and usually 20 mm diameter anchor bolts are usually considered. So the anchor bolt is basically a bearing type of bolt only, so it must have a minimum end distance, otherwise sufficient end distance there will be failure. So there has to be a minimum end distance from the end of this base plate towards the center of bolt hole, and also from this bolt hole to the end of the eye section also. So we have to see whether the minimum end distance is there. Now when we go to clause 2.4.2, sorry, 10.2.4.2, so clause is basically, there is a 10 also in this clause, because in design of connection is in clause 10.2.4.2, and there the minimum edge distance is given as 1.5 times the diameter of bolt hole. So for 20 mm bolt, the diameter of hole has to be 22. So obtained from table 19 of page 73, 2 mm clearance. So the minimum end distance has to be 33. Now the projection required will be 2 times that of the end distance, because in bolt hole front and back, so it will be 2 times 33, it will be 66. So our obtained value of the 34.27 will not be sufficient, so we have to provide a projection of 66 millimeter. So the length of the base face will be 350 into 2 times 66, and breadth will be 250 into 2 times 66. And finally we will obtain a length of base plate as 482 and the breadth of base plate as 382. So the length of the base plate now becomes 350 plus 2 times 66, because we have to provide projections on either sides. So it will be 482 mm, and the breadth of the base plate will be 250 plus 2 times 66, it will be 382. So we have this as to provide the area of base plate, and this area when we multiply it will be 1.84 into 10 raised to 5. This is greater than 1.33 into 10 raised to 5, hence it will be safe. Now we have to also calculate the thickness of the base plate. So it is given in clause 7.4.3.1, and it is given like minimum thickness of the rectangular slab bases is given by this equation, where Ts is equal to the square root of, this is whole square root of 2.5 times W multiplied by a square minus 0.3 b square into gamma m square, the whole divided by f5, and this has to be greater than the thickness of the flange of the ISMB 350 HB 350. So W will be the actual bearing pressure due to the area which we calculated at the last, which is 1.85. So we'll be calculating the new bearing pressure as the load divided by the area, and we'll be getting 8.152. So load is factored load, which is 1500, and this is the actual area which we calculated for the slab base, which is 1.84 into 10 raised to 5, and this will be our actual bearing pressure, that is a uniform pressure below which the slab under the axial load. And A, B are the larger and smaller projections. So in our case, both these projections are having 66 mm only, so both will be same. Gamma m0 will be the factor of material partial safety factor obtained from table 5, which is 1.1, and Fi value will be the yield stress, which is 250. So when we substitute all this value in the to find the minimum thickness of slab is as per clause 7.4.3.1 in page number 47, 2.5 times 8.152 into 66 square minus 0.3 into 66 square multiplied by 1.250, we will be getting a value of 16.53, and we will be rounding to the nearest commonly available base plate thickness, which is 18 mm, and this is greater than our thickness of flange, which is 11.6. So This is obtained from IS 808, which I have written earlier also. TF is the thickness of flange only. Hence, our number is safe. So we have to provide a base plate of size 482 by 382 by 18 mm and provide an anchor bolt of 20 mm dia for 300 mm long. 2 or 4 number of anchor bolt we have to provide, so that we have fixed this base plate to our pedestal, and we can use welded connections for fixing this our column to the slab base. So in question we have to design a connection as a welded connection that is been given. So we will be designing this question for designing as a welded connection. So we know that the welding will be provided along the sides of this ISHB. So all the sides we have to this red marked areas are the area where we will be welding throughout the members, and we have to provide it around ISHB 350 at 67.4. So first we have to find the total length of the weld, that is the LW value. So here this will be 250, this will be 250, that is 2 times 250, and this length will be 350, so that we can cover also we can cover this length also, this small area also will be covered. Okay, so this will be like this length plus this length plus this length will be 350, this length plus this length plus this length will be, that's 2 times 350. Now there is this length remaining. Okay, now this is the thickness of the web, which is 8.3, so we have to reduce that. So 2 times 250 minus this length, that is written here. So when we substitute all these things, we'll be getting the length of the weld as 16.1683.4, sorry, 1683.4 mm, 1683.4 mm as the total length of the weld. In length we have to basically design for the length and size of the weld, that's basic two parameters. So determine the size of the weld, we have to go to the find the design strength of the fillet weld. Basically we are designing for fillet weld, so we have to go to page number 75. So usually in section 10 is the section where we study about the various details of connections like bottle connection, welder connection. And when we go to page number 79 and when we go to clause 10.5.7, we will see the under the fillet weld heading, that is 10.5.7.1.1, which is in page number 79. The design strength of the fillet weld FWD will has to be equal to FW1 divided by gamma MW, and where FW1 will be FU divided by root 3. And there the explanation for FU is also given, that is FU has to be the smaller of the ultimate stress of the weld or the parent material. So we assume the weld material and parent material is same. The parent material is Fe 410, so it is having a ultimate strength of 410 Newton per mm square. Gamma MW, when we look at table 5 in page number 30, we are assuming it to be a shop weld because we assume this member we will be welding at shop, so its factor is 1.25. If it is given the question it has to be welded site, then we have to assume it as 1.5. For the time being I assume it to be 1.25. Now we have to substitute these values in this equation, that is FWD will be FW divided by gamma W, so 410 divided by root 3. So how we obtain this equation is, so what we do, I will substitute this equation over here. So basically FWD will be equal to 410 divided by root 3 into 1.25. So finally we will getting an answer of 189.37 Newton per mm square. This will be the design stress of the fillet weld. Now we have to find the total area of the fillet weld, because based on the load we have to find the area. So the area can be obtained from the next class, which is clause 10.5.9. we can see the stresses due to individual forces, and we can see the normal stress due to axial force Fs will be equal to P divided by Tt into Lw. So basically for a weld, the important thing to be noted, the weld has a length, effective length, which is Lw, and it has a throat thickness, and throat thickness which we have studied in the design of weld. When we multiply that to, it will give you the effective weld area. The effective area of the weld will be resisting the load which is coming to the connection. Okay, so the load which is coming to the connection is the compressive load which is given in the question, which is 1500 kilonewton, and we have calculated the stress which can take for this weld which we assume, which is 410 grade weld, and from by dividing load divided by stress we will be getting the effective area of the weld, which is throat thickness into length of the weld. So we have calculated, just now calculated the effective stress of the weld from our clause 10.5.7.1.1, and we know the load which is given in the question itself. So when we take the ratio, that is 1500 divided by 1837, we will give the total area which is required for the weld, 7921 millimeter square. And the area which we know not, because this is a member. Okay, I will draw the member again to change confusion. Okay, and over that we will be providing the weld. Okay, this will be the weld, and this thickness is called as the throat thickness. Basically this is the size of the weld. Okay, that tt into length of the weld. So length of the weld is a weld, that is this thing. So when I take all the sum, this will give you the length of the weld, and multiplied by throat thickness, tt will give you the area. Now we, to find the throat thickness, we already know the area, and we already know the lw, which just now we calculated. Okay, now the throat thickness will be the area divided by the lw. Okay, now we will get the throat thickness of 4.705. So we know the total area from our this calculation by load by weld stress, which is FWD, and we already know the total effective length of the weld, which is 1683.4. So basically we can easily calculate the throat thickness. TT will be effective area divided by LW. So we get the throat thickness as 4.705 mm. Now from that we can calculate the weld size. So that is a design how we do the weld connection. So we know that for fielded weld, the throat thickness will be always K times the size of weld. So this is actually given in our clause 10.5. Sorry, it is not, it is given in, actually it is not given in, not it is 10.5.3.2. So if you go to page number 78, when we refer the 10.5.3.2 clause, when you read that, so it is given as the effective throat thickness shall be K times the fillet size. So it is TT will be K into S. Now what's the value of K? When we go to our table 22, for different fusion angle. So what is this angle? Fusion angle basically means the angle between the two members. So this is our column base end and this is our slab base end. So this angle will be always 90 degree. So this is perfectly like a side of a rectangle. Now if you go to table 22, for 60 to 90 degree angle of fusion phase, the value of K will be always 0.7. So TT will be 0.7 into S. So what will be S? TT divided by 0.7. So 6.72. So we'll provide a 8 mm size weld. So that's how we design the weld connections. So weld connection design basically means we have to design the length of the weld and size of the weld. Now we will check whether this provided weld size is there. This is an optional part. We can do it or not, but we always know what is the minimum weld size is based on table 21. It gives based on the thickness of thicker member. We know that our base plate thickness is 18, and from that we'll be selecting the 5 mm as the minimum weld size, and maximum weld size is given in class 5.8.3, which is the thickness of the member which is to be connected, that is minimum thickness of the member, and it is ISHB and base plate, and from that the minimum thickness was the thickness of weld, which is 8.3, and the assumed value of 8 mm is in between these two values, that is 5 and 8.3. So the weld size is safe to provide. So this is how we design a welded connection for a column base which is to be connected to a column which is to be connected to a slab base.